Today we get to do some actual physics. Last chapter 1, was about the mathematical foundations that we need to do physics. And this chapter is about physics. It is actually a combination of chapters 2 and 3 combined into one. So we'll spend about 3 days working through all this material. And the reason for combining the two chapters, chapter 2 in the textbook deals with motion in 1 dimension. Chapter 3 deals with motion in 2 dimensions. But a lot of the definitions and concepts look almost identical, and to reduce the number of concepts that you need to learn, I've combined them into a single chapter. So what we'll be talking about is called kinematics. It is the subject that deals with concepts needed to describe the motion itself, how it moves through, how an object moves through space. And that's chapters 2 and 3. Chapters 4 through 7, just to introduce where we're going with the next several chapters, deals with the effect of forces. If you push on something, then what's the resulting motion? All the forces that act on objects. And kinematics and dynamics together make a subject called mechanics. It's a subject that I luckily will be able to introduce you to here today. It's dealt with in much more detail in the intermediate mechanics course, which I also teach here at Utah State, as well as in a graduate course. So there's all different levels of mechanics. The Blue Angels perform their maneuvers that involve displacement, velocity, and acceleration. That's kinematics. So we're not worried about the air forces and that sort of thing on the wings of the Blue Angels, but how they move through space. So, section 3.1 of the textbook deals with these 3 concepts, the displacement, the velocity, and the acceleration. And I've divided this into 4 parts, and so this is the first of the 4 parts. So the basis for everything is the position vector. We've talked about vectors in chapter 1. This is a very special kind of vector. And the concept is to define the position vector, its components, and its magnitude. So I'd like for you to commit to memory both these words here and these equations down here. Together they give a complete understanding of the position vector, and they do complement each other. The position vector of an object points from the origin to the object's current location. So shown here in this coordinate system, this is x and y axes. The z-axis would be coming out of the screen. The origin is this spot right here. It's called the origin, or the origin of coordinates. It's where x equals 0 and y equals 0. So this position vector points from that origin, from here, to the current location of the object. It's denoted by this dark blue arrow, and its symbol to represent the position vector is lowercase r. And as usual, we'll put that in boldface and put an arrow over the top of it. So here it is in equation form. This is the position vector. It's measured in meters. So when you see this guy out to the right in a concept, in something in parentheses, it's talking about the units that this object is measured in SI units. And in this case, it's meters. A position vector is expressed in meters. And this part here are the components of this vector. The components are x in the x hat direction. If you recall from the last chapter, x hat, that's a little hat on top of the x, points in the x direction, and it has a magnitude of 1. It's a unit vector. And y hat is a little unit vector that points in the y direction. And whatever, as we talked about in chapter 1, Whatever multiplies x hat is the x component of a vector. So that's this piece right here, the component of the vector r that points in the x direction. In the past, in chapter 1, we would have denoted that r sub x. Like we had vector a, and we had a sub x and a sub y for the x and y components of a vector a. We don't use this notation here, and the reason is that the x component of r is just the x coordinate of the object as it moves through space. So this is the current location of an object with coordinates x and y, like you've already discussed in your math classes. The y component is y. Now note here that I've got the y component marked over here, but I can take this same vector, this light blue vector, and move it over to here and have y be the length of that component, and then it's more clear to you then that this component is just the value of y. All right, those are the components. That's the position vector. What is the magnitude? The magnitude of the position vector is like the magnitude of any other vector. We did a lot of problems in chapter 1 thinking about magnitudes. How do you find it? Well, the magnitude is denoted by an italic letter, not in boldface, and it represents the length of this vector. Well, you say, well, hang on, that just looks like the hypotenuse, and sure enough, it is. It's the hypotenuse of that vector, of this right triangle, with sides x and y. And we can certainly just apply the Pythagorean theorem to come up with the magnitude of that vector, r. So just to make sure that we've covered everything, its components are the Cartesian coordinates of that location. That's this x and y. It says x, you might not be able to read it very well. Its magnitude is the distance, r, from the origin to that current location. And you might say, well, hang on now. In the position vector, as an object moves around through space, that position vector changes with time. And I say, it sure does. Because when the object is moved over to here, say, then that position vector points here. So that position vector is going to follow objects as they move around through space. Concept 3.2, define the displacement vector. And this one calls to mind not the position of an object, but about how much it's moved. If I've been displaced from my home, I've been moved from my home. And so we're not so concerned about exactly where it is, but where it's moved. So the displacement vector will become important as we define the velocity vector. So we want to define the displacement vector, its magnitude, its components, and the elapsed time. The displacement vector points from the initial position of an object as it moves around through space to the final position of the object. So for example, if we have an initial position of this race car here, given by this position vector r naught. So we use the subscript 0, we call it naught, and it almost always means initial position. So this is the initial position vector, points from the origin to the initial location of the object. And then r, the vector r, without a subscript, points from the origin of coordinates to the final location. And these two could be, and shown here also are the clock times between the initial and the final. So it looks like if this is the second hand, it's about 5 seconds here, it's about 20 seconds here. So there's about 15 seconds worth of elapsed time between the initial and the final positions. So what's the displacement vector? These are just position vectors as it follows this race car through time. It points from the initial position here to the final position here. So that is my displacement vector. And so it doesn't start at the origin like the position vector does. It starts at the initial position, whatever you designate as an initial position, and it ends at the final position. Well, let's look at it, see if we've got everything here. Its magnitude is the straight line distance. Okay, so the magnitude of it, we're going to denote with this, and by the way, this symbol right here is the Greek letter delta. That's this triangle shape, is the Greek letter delta. And it almost always, in this class, I think it always will mean the final minus the initial. So here is the mathematical definition of the displacement vector. It's consistent with this graphical representation of the displacement vector, but it has a little bit more teeth to it. The displacement, delta r, the change in r, so delta r is the displacement vector, and that means the change, and the change in so it's the change in, which is the final minus initial, is the final position minus the initial position. Final minus initial gives a displacement vector. Let's verify that that is actually true with our knowledge of graphical addition of vectors. Let's take a look at this. If delta r points from here to here, and r naught points from the origin to the initial position, then I can add r naught to r, to delta r, this Greek letter delta, and get r, the final position. Let's write that down. R equals r naught plus delta r. Graphical addition of vectors, where you add the tail of the second vector to the tip of the first vector, and then draw the resultant vector from the tail of the first to the tip of the second, says that this is the equation that relates those three vectors. Well, is this equation consistent with this one? Are these two equations consistent with each other? Well, actually they are. What if you subtract r naught from both sides of this equation? Then on the left side we'll have r minus r naught, and on the right side of the equation these r naughts will cancel each other and we'll just get delta r. Well, that is this. Delta r is r minus r naught. So what we've done is that we have shown just now that this mathematical definition of the displacement vector, being the final position minus the initial position vector, is consistent with this graphical representation where the displacement vector goes from the initial position to the final position. This is just a review. The final position vector can be written in terms of components as x hat plus y hat. That just says that its components, components of this vector are x in the x direction and y in the y direction. The component of r naught, its components are x naught and y naught. And the reason that we want to do this is that now we're starting to see the power that you can get from a graphical analysis and from this vector calculus actually. So if we substitute this r into here and this r naught into here, then we see that delta r is x hat plus y hat that's the r that we substituted in, minus x naught x hat plus y naught y hat. All right, and that says that if we put the terms together that involve x hat, we'll have x minus x naught times x hat plus y minus y naught y hat. Well, that just says then that the displacement vector, the change in x is x minus x naught. So that's the x, this is the x component of the displacement vector. We'll do a lot of examples with this, and so if it seems a little much right now, we'll do a lot of examples to show you how this comes out. Delta y is the y component of the displacement vector. We're also supposed to define the elapsed time. And let's see if you can see why this definition makes sense based on how we've been talking about the delta, Greek letter delta. Delta means final minus initial. And now we're talking about time. So the change in the time, the final minus the initial, is going to be the final time, t. That's this time up here at the final position, minus the initial time, t naught, t minus t naught. And certainly, that's this 15 seconds that we talked about between the initial reading of the second hand and the final reading of the second hand. And we have, and it means, I mean, you would have said, well, yeah, that's what makes sense. It's from that time to that time. It's an elapsed time. It makes good sense. Final time and initial time. Okay, which one of the following statements concerning the displacement of an object is false? Let's go through these one at a time. But at this juncture, I would like to actually encourage you. This is the first clicker question that we're going to talk about in this chapter. If we were doing this live in a classroom, I would let you guys ruminate on this and think about it and work together on it, try and come up with the answer. But I would encourage you, as you're watching these videos, to pause the video, take a look at the screen, see if you can answer the question. Then resume the video and see if the discussion is consistent with your thinking. Why? It moves you forward into an active learning mode instead of just passively taking down information. So pause the video, give it a try, see if it works for you, and then come back. Okay, now we're back. Which of the following statements concerning the displacement of an object is false? Well, let's look at them. The displacement is a vector quantity. That's certainly true. That points from the initial position of an object to its final position. True or false? Well, that's actually true. Points from its initial position to its final position. Remember, the displacement vector doesn't start at the origin. That's a position vector. All right? The magnitude of an object's displacement is always equal to the total distance it travels from its initial position to its final position. True or false? That's false. Why? Because in the car example that we talked about, the initial position of the car was here, and the final position of the car was there. The displacement vector measured the straight line distance between those two. The magnitude of the displacement vector is the straight line distance as the crow flies between this initial position and this final position. It's along that line. It's not the actual distance it's traveled. It's a straight line distance. So that one, in fact, is the false one, and that's the one we're looking for. Let's look at the other ones, though. The direction of an object's displacement is indicated by an arrow that begins on the initial position of the object and then ends on its final position. True. The length of the arrow representing the object's displacement is proportional to its magnitude, which represents the straight line distance between the positions. Also true. Great.